Okay, so now we're going to talk about the basic properties of logs. So composing inverses and recognizing those. So here's something that's kind of key is remember that logs are the inverse of exponential functions. So if f of x equals b of x, f inverse of x would be the log base b of x. So remember y equals b to the x equals log base b of y. So in recognizing that they're inverses means that you're going to see things where they compose the inverses, that is, they take, say, f of f inverse of x, right? Or they take f inverse of f of x, and what happens is you should just get the independent variable back. That is, they cancel each other out. Simple in concept, it looks tricky though. So there's basically two different ways that this is going to look. So let's say that we had g of x. Well, let's just say we had an expression we want to simplify. So let's just make this really easy on ourselves. What if we had 2 to the log base 2 of 5? What does that equal? So looking at this, hopefully you see two functions being composed. Hopefully you see a 2 being raised to some power, and you see a log base 2 of, well, in this case it's 5, but of something, right? So one of your functions, the outer function, if you will, that is, if you looked at this, the first thing that you do is you do the log base 2 of 5, right? So that would be your inner function, aka log base 2 of x. And then the outer function, the last thing you do is 2 to the exponentiate base 2. Oh, there's a fun word. Exponentiate means raise to the, make an exponent of, and then you say of a certain base. So exponentiate base 2 would mean exponent, you're making 2 to some power, right? But in any event, if this were f of x, then, well, these are inverses, right? Log base 2, right? So what you're really looking at is f of f inverse, which we know to, now in this case they have not plugged an x in, they've plugged in a 5, which means that the result here is 5. So another example might be e to the natural log of 7x plus 3. Well, that looks nightmarish, right? Who the heck knows what the natural log of 7x plus 3 is? But e to the x, something of that form, these are two things being composed. So what happens is they cancel, and your final answer is 7x plus 3. Okay? We're going to talk about, there's a caveat to what x can be in this case, but we'll talk about that here in just a sec. So this is one way you might compose these, okay? The other way is if you make the inner function the exponential. So let's say that we had the log of 10 to the 3x, okay? Now, we're going to look at some properties that can help us deal with this too, but thinking about this, first off, we know that this is a common log. If I don't write this, then we know that this is base 10, right? Which means that we're looking at the log base 10 of something, and we're looking at 10 to the something. Maybe I shouldn't use x. I've already supposed to say y, and then 10 to the y, right? So these two are being composed. In this case, this is the log composed with this. So they cancel, and that means that our final answer is 3x, right? It's a relatively simple concept. It just gets a little bit confusing when you are presented with it from time to time. So if you had the log base 2 of 2 to the 5th, well, it turns out you could actually figure that out, right? 2 to some power equals 2 to the 5th, and that's relatively obvious. Or you could recognize that they're inverses. So one way to go is you recognize they're inverses, cancels out, you're left with 5. Or you can say, hey, wait, log base 2 to the 5th. I can rewrite that in exponential form, meaning this is going to be 2, so this is going to equal some exponent we don't know, right? So the base is 2 raised to the exponent equals 2 to the 5th, and at this point it becomes matching. This is, Sesame Street. One of the, these, how is this like this? Well, that would mean that x has to be 5, which means your answer would be 5. Either way works, okay? What a log can and cannot be. So remember that when you're looking at a generic exponential function, b's got to be greater than 0. You're looking at, let's just say it's growth for argument's sake. Let's say b is greater than 1. We're looking at something like this, yes? Which means that when we're looking at a log base b, right, of x, then it's the inverse. It's a reflection over that line, which means that there's certain restrictions to this, okay? Remember, the domain for an exponential is, well, negative infinity to infinity, right? Meaning any possible x can be plugged in. Doesn't matter. Positive, negative, 0 is okay. But the range has got to be strictly greater than 0, right? Meaning 0, soft, right? This is x is greater than 0. And if you remember from these being inverses, because they are, right? That would mean that the domain and the range switch. Just like that. So this means that if someone asks you to find the log of negative 3, right, you can say DNE, which is short for does not exist. Because if you look at the independent variable here, the x that we're plugging in, it's got to be between 0 and infinity, right, and can't include it. So just be on the lookout for that. Now, thinking back to that last problem, there are some other things that could happen. Like if you were asked to solve log of 2x, right, then you know that 2x itself, right, we're taking the log of 2x. By the way, if I write it like this, or if I write it like this, it means the same thing. I'm taking the log of all of 2x. You couldn't really solve this unless you had some sort of variable. So let's say we knew that log of 2x equals 7, right? You could rewrite this as an exponential equation, right? Meaning this is a log base 10 because it's not written. So this would be 10 to the 7th, the log equals an exponent, equals 2x, right? So then 10 to the 7th x, you just take 10 to the 7th divided by 2, and there's your answer, right? 10 to the 7th is a 1 with 7 zeros, so what, 10 million divided by 2, so this is like 5 million. Yay, right? One thing to remember, though, is 2x, that is, this has to be greater than or equal to 0. Now, 10 to the 7th divided by 2, it is going to be. So if someone asks you to do something like log base 2, let's say log base 3 of x equals negative 9, could you do it? Well, let's see. That is same as 3 to the negative 9th equals x, yes? Base exponent equals the value. What is 3 to the, oh, wait. Remember, 3 to a negative exponent, and this will be your downfall if you don't recognize it. 3 to a negative exponent is going to be just the reciprocal, so it's 1 over 3 to the 9th. So it turns out this is possible to solve, okay? You just have to make sure that whatever you've got is positive. In this case, it will be. So is it possible to take the log base 3 of something and get negative 9? Well, they're telling you that you're taking something, right? And when you do 3 to that exponent, that's what you're getting, okay? So that would be your answer, all right? Domain and range, I think I already talked about this, but please bear in mind that logarithmic graphs tend to look like this, okay? Now, this point here is the x-intercept, and so there's a corresponding y-intercept to the inverse. So, like, what does that look like? Like, if you're looking at y equals log x, what does that mean? Well, here, the y value is 0, right? So the y value is 0, because we know this is some point we don't know, comma 0. Otherwise, it wouldn't be an x-intercept, yes? Well, let's see. So that's log base 10, so that's 10 to the 0th equals x. Anything to the 0 is 1. So in an unmodified log like that, so like if you're looking at the graph of y equals log base 3 of x, the same thing happens. If you set that equal to 0 to figure out where it crosses the x-axis. And the reason we have an x-intercept is because we don't have a y-intercept. This is an asymptote, right, at x equals 0. So log base 3 of x, that would be, well, there's the base, equals the exponent, like that, okay? So it still ends up being 1. So they have y-intercepts of 1. Does that mean, or sorry, x-intercepts of 1. Does that always mean the x-intercept's 1? No, because it could just be something beyond a plain old log, right? It could be 2 times the log of, and then that would influence the answer, of course, right? Okay, so let's take a look at using Desmos to calculate logarithms. Now, Desmos itself is very useful, but you got to be careful when you're actually calculating logs. To actually type this in, so you could type in a log, right? I believe you could type in log of 100, and you get a value 2. Now, please note that that is a common log, nothing written. So that's log base 10, okay? If you want to do a log of another base, you can. You got to go down here to functions, and you go over to miscellaneous, MISC, right? And it's got 3 different log buttons. Natural log, log base E, log base 10, and then log base, it's very hard to see, but that's a little A. So if you type that in, it does that subscript thingy, and that means that you could take the log base 3 of things like 81, which, well, all right, it wrecked the surprise, because as soon as I type it, I don't have to let equals or anything. It's kind of horrible. But that means 3 to the 4th equals 81, right? And so if you try something like log of -5, it says undefined. Or what about log of -5? Still undefined. How about negative log of 5? Well, that's a value, right? Because you're taking -1 times that. But you can do this, or you can do natural logs, like what's the natural log of E, right? Raised to the 17th. Why is that? Hey, those are inverses, remember? So the natural log and the base E, they cancel out, okay? So that's how you can use Desmos to help you with log calculations. And we'll do examples next, but this concludes a little more about the properties of logarithms.